The following lecture is one of a series that covers the HNC Electrical Engineering Unit FY 9E DC and AC Principles. This lecture provides a basic introduction to capacitors and presents a number of techniques to analyze capacitive circuits that have combinations of series and parallel elements. The subject elements to be covered in this lecture are as listed on this slide. A summary of all the information covered, the worked examples, and a set of self-assessment questions are contained in the accompanying workbook. When a source is connected across a pair of parallel metal plates, charge will start to flow. Leaving the plate connected to the positive terminal with a positive charge and the plate connected to the negative terminal with a negative charge. Charge will continue to flow until the force across the plates is equal to the supply voltage, so Vs equals Vc. A device capable of storing charge in this fashion is called a capacitor. The resultant force across the charge plates of a capacitor may be explained by the presence of an electric field, termed an electrostatic field, as it is generally unchanging. An electrostatic field is defined as a region in which a positively charged particle would experience a force. The field is indicated by a series of lines between the plates. These lines are called the electric flux and are referenced by the Greek letter psi. The strength of the field is indicated by how closely the lines are packed together, termed the line density. The direction of the force on the positively charged particles, and hence the direction of the field, is indicated by the arrowheads, which are pointing towards the negatively charged plate. Capacitance is the term given to the ratio of the amount of charge stored to the applied voltage for a specific device. The amount of charge a capacitor can store for a given voltage is termed its capacitance. The more charge a device can store, the greater its capacitance. The symbol associated with capacitance is the letter uppercase C, and its unit is the farad, abbreviated to the letter uppercase F. A capacitor is represented in a circuit diagram by the symbol shown. There is a relationship between capacitance, charge, and voltage. The highlighted box shows capacitance is equal to the charge divided by the voltage. Provided the charge is in coulomb and the voltage is in volts, then the capacitance calculated will be in farads. This relationship, termed the formula throughout the rest of this lecture, is the capacitive circuit equivalent to Ohm's law. The following example is in the accompanying workbook, Capacitive Circuits, Capacitance. Here we have been asked to find the value of capacitor that can store a charge of 20 microcoulomb with an applied voltage of 50 volts. From the formula, we know that the capacitance C is equal to the charge Q divided by applied voltage V. Substituting the values, C equals 20 times 10 to the power minus 6 divided by 50, which equals 0.4 microfarads. It does not matter what part of a capacitive network is examined, the capacitance formula always holds true. The formula enables that for any given situation where two of the three electrical factors are known, the third to be derived. Using the triangular representation of the formula, if the voltage and the capacitance are known, the charge may be determined. If the charge and the capacitance are known, then the voltage across the device may be found. If the voltage and the charge are known, then the capacitance may be calculated. A parallel circuit is one in which the noses of all the elements are connected together and all the tails are connected together. So in the circuit fragment shown, the three elements C1, C2 and C3 are connected in parallel. The potential arrow indicates the voltage V across the circuit terminals. It should be noted that in a parallel circuit, the voltage across each branch will be the same, although the amount of charge stored on each capacitor will depend on its capacitance. By inspection, the total circuit charge Q must equal the sum of charge stored in each branch capacitor Q1 plus Q2 plus Q3. Applying the formula, Q equals V times C1 plus V times C2 plus V times C3. Taking out V as the common factor, Q equals V times C1 plus C2 plus C3. Dividing through by V, Q divided by V equals C1 plus C2 plus C3. Since Q is the total circuit charge and V is the applied voltage, then by definition this must equal the total circuit capacitance Cp. An equivalent of the parallel circuit may therefore be drawn where capacitors C1, C2 and C3 are replaced by a single capacitor Cp. The highlighted formula shows that where there are a number of capacitors connected in parallel, they may be replaced by an equivalent capacitor Cp, where Cp is equal to the sum of the individual capacitors. The following example is in the accompanying workbook, Capacitive Circuits, Parallel Circuits. Here we are required to determine the total capacitance of the circuit, the voltage across the circuit, and finally the charge on each capacitor. To find the total circuit capacitance. The total capacitance of a parallel connected circuit is the sum of all the individual capacitors. Substituting the values, Cp equals 1 times 10 to the power minus 6 plus 3 times 10 to the power minus 6 plus 5 times 10 to the power minus 6, which equals 9 microfarads. To find the voltage across the circuit. From our formula, we know that the circuit voltage equals the total circuit charge divided by the total circuit capacitance. Substituting the values, V equals 90 times 10 to the power minus 6 divided by 9 times 10 to the power minus 6, which equals 10 volts. To find the charge on each of the capacitors. Since we know the value of each capacitor and as they are all in parallel, they will all have the same voltage, we can use our formula to determine the charge on each capacitor. Applying the formula, Q1 equals C1 times V. Substituting the values, Q1 equals 1 times 10 to the power minus 6 times 10, which equals 10 microcoulomb. Applying the formula, Q2 equals C2 times V. Substituting the values, Q2 equals 3 times 10 to the power minus 6 times 10, which equals 30 microcoulomb. Applying the formula, Q3 equals C3 times V. Substituting the values, Q3 equals 5 times 10 to the power minus 6 times 10, which equals 50 microcoulomb. We can do a check on the answer at this point, since we know that the sum of Q1, Q2 and Q3 should equal the total charge Q stored in the circuit. Substituting values, Q equals 10 times 10 to the power minus 6 plus 30 times 10 to the power minus 6 plus 50 times 10 to the power minus 6, which equals 90 microcoulomb, the total circuit charge. Parallel circuits may also be considered as a means of dividing the total circuit charge between a number of capacitors. Consider the parallel circuit shown. Using the formula to determine the circuit voltage, V equals Q divided by Cp, where Cp is the total circuit capacitance. So to calculate the charge on C1, Q1 equals C1 times V. Substituting for V, Q1 equals C1 times Q divided by Cp. This can be rewritten as Q1 equals Q times C1 divided by Cp. Similarly, Q2 equals Q times C2 divided by Cp, and Q3 equals Q times C3 divided by Cp. The highlighted boxes shows the total charge divides among the parallel branches in the ratio of the branch capacitor to the total capacitance. The following example is in the accompanying workbook, Capacitive Circuits, Charge Division. Here we are required to determine the charge on each branch capacitor using charge division. The formula to calculate Q1, the charge on capacitor C1, is the total circuit charge Q times the branch capacitor C1 divided by the total circuit capacitance Cp. We know the value of Q and C1, but we need to calculate the value of Cp. So, Cp equals C1 plus C2 plus C3. Substituting the values, Cp equals 1 times 10 to the power minus 6 plus 3 times 10 to the power minus 6 plus 5 times 10 to the power minus 6, which equals 9 microfarads. Now we can continue to calculate the charge on each capacitor using charge division. So Q1 equals Q times C1 divided by Cp. Substituting the values, Q1 equals 45 times 10 to the power minus 6 times 1 times 10 to the power minus 6 divided by 9 times 10 to the power minus 6, which equals 5 microcoulomb. And Q2 equals Q times C2 divided by Cp. Substituting the values, Q2 equals 45 times 10 to the power minus 6 times 3 times 10 to the power minus 6 divided by 9 times 10 to the power minus 6, which equals 15 microcoulomb. Finally, Q3 equals Q times C3 divided by Cp. Substituting the values, Q3 equals 45 times 10 to the power minus 6 times 5 times 10 to the power minus 6 divided by 9 times 10 to the power minus 6, which equals 25 microcoulomb. A series circuit is one in which all the elements are connected nose to tail. So in the circuit fragment shown, the three elements C1, C2 and C3 are all connected in series. When the source is connected, a current will flow, building up the same charge on each capacitor until the sum of voltages across each of the capacitors equals the supply voltage. So V equals V1 plus V2 plus V3. Applying the formula, V equals Q divided by C1 plus Q divided by C2 plus Q divided by C3. Taking out Q as a common factor, V equals Q times 1 over C1 plus 1 over C2 plus 1 over C3. Dividing through by Q, V divided by Q equals 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. Since Q is the total circuit charge and V is the circuit voltage, then by definition this must equal not the total circuit capacitance CS, but 1 over CS, i.e. the reciprocal of CS. The actual value of CS may finally be determined by simply taking the reciprocal of this result. An equivalent of the series circuit may therefore be drawn where capacitors C1, C2 and C3 are replaced by a single capacitor CS. The highlighted formula shows that where there are a number of capacitors connected in series, they may be replaced by an equivalent capacitor CS, where the reciprocal value of CS is equal to the sum of the reciprocal values of the individual capacitors. The following example is in the accompanying workbook, Capacitive Circuits, Series Circuits. Here we are required to determine the total capacitance, the total charge in the circuit, and the charge on and the voltage across each capacitor. To find the total circuit capacitance. The reciprocal of the total capacitance of a series-connected circuit is the sum of the reciprocals of all the individual capacitors. Substituting the values, 1 over CS equals 1 over 1 times 10 to the power minus 6, plus 1 over 3 times 10 to the power minus 6, plus 1 over 5 times 10 to the power minus 6. which equals 1.53 times 10 to the power 6. That is the reciprocal of CS. So CS equals 1 divided by 1.53 times 10 to the power 6, which equals 0.652 microfarads. To find the total circuit charge Q. From our formula, we know the total circuit charge Q is equal to the total circuit capacitance CS times the voltage across the circuit V. Substituting the values, Q equals 0.652 times 10 to the power minus 6 times 10, which equals 6.52 microcoulomb. To find the charge on each capacitor. Since the capacitors are all in series, they all have the same charge of 6.52 microcoulomb. As we know the value of each capacitor and its charge, we can use our formula to determine the voltage across its terminals. So V1 equals Q divided by C1. Substituting the values, V1 equals 6.52 times 10 to the power minus 6 divided by 1 times 10 to the power minus 6, which equals 6.52 volts. And V2 equals Q divided by C2. Substituting the values, V2 equals 6.52 times 10 to the power minus 6 divided by 3 times 10 to the power minus 6, which equals 2.17 volts. Finally, V3 equals Q divided by C3. Substituting the values, V3 equals 6.52 times 10 to the power minus 6 divided by 5 times 10 to the power minus 6, which equals 1.3 volts. We can do a check on the answer at this point, since we know that the sum of V1, V2 and V3 should equal the total voltage across the circuit V. Substituting the values, V equals 6.52 plus 2.17 plus 1.30, which equals 9.99 volts. This video clip is a simulation of the example and shows how each capacitor voltage would be measured in practice. A DMM is connected across each capacitor set to read DC volts. When the switch is closed, the DMM values are the same as those calculated within experimental limits. Complex capacitive networks will normally have capacitors in both series and parallel, and whilst it may not always be necessary, sometimes the only way to fully analyze a circuit is to reduce it to a single element. There are 3 key reduction steps. First, deal with the simple series branches. In this case, there is just one set of series elements, CS. This reduces the circuit as shown in step 1. Next, deal with the simple parallel branches. Again, there is only one parallel branch, CP. This reduces the circuit as shown in step 2. Then keep repeating steps 1 and 2 until only one element is left. In this case, we only have a set of series elements to consider which equate to CT. Finally reducing the circuit to a single element. The following example is in the accompanying workbook, Capacitive Circuits, Circuit Reduction Techniques. Here we are required to determine the total circuit capacitance, the total circuit charge, the charge on and the voltage across each element. To find the total capacitance CT using the key reduction steps. Step 1. Deal with the simple series branches, CS. So 1 over CS equals 1 over 3 times 10 to the power minus 6 plus 1 over 5 times 10 to the power minus 6, which equals 0.533 times 10 to the power 6. This is the reciprocal of CS. So CS equals 1 divided by 0.533 times 10 to the power 6, which equals 1.88 microfarads. Step 2. Deal with the simple parallel branch CP. So CP equals 1.88 times 10 to the power minus 6 plus 4 times 10 to the power minus 6, which equals 5.88 microfarads. Step 3. Repeat steps 1 and 2 until only one element is left, CT. So 1 over CT equals 1 over 2 times 10 to the power minus 6 plus 1 over 5.88 times 10 to the power minus 6, which equals 0.670 times 10 to the power 6. That is the reciprocal of CT. So CT equals 1 divided by 0.670 times 10 to the power 6, which equals 1.49 microfarads. To find the total circuit charge Q. Applying the formula to the equivalent circuit from step 3, so Q equals CT times V. Substituting the values, Q equals 1.49 times 10 to the power minus 6 times 20, which equals 29.8 microcoulomb. Looking back at the equivalent circuit obtained in step 2, if the charge on the 1.49 microfarad capacitor was 29.8 microcoulomb, then this will also be the charge on the 2 microfarad and the 5.88 microfarad capacitors, as in a series circuit the charge on each capacitor is the same. To find the charge on each of the 2 branch capacitors in step 1, the series group shown as C1 and the 4 microfarad shown as C2 by using charge division. The charge division formula to obtain the charge on C1 is Q1 equals Q times C1 divided by CP. From the equivalent circuit obtained in step 2, we know the total charge stored in the parallel group Q is 29.8 microcoulomb. The total capacitance P of the parallel paths is 5.8 microfarads, and the value of C1 is 1.88 microfarads. Substituting the values, Q1 equals 29.8 times 10 to the power minus 6 times 1.88 times 10 to the power minus 6 divided by 5.88 times 10 to the power minus 6, which equals 9.53 microcoulomb. We can use the charge division formula again to find the charge on the 4 microfarad capacitor C2. So Q2 equals Q times C2 divided by Cp. Substituting the values, Q2 equals 29.8 times 10 to the power minus 6 times 4 times 10 to the power minus 6 divided by 5.88 times 10 to the power minus 6, which equals 20.3 microcoulomb. Now to find the charge on each capacitor. From step 1, we can see the charge on the 2 microfarad capacitor is 29.8 microcoulomb, and on the 4 microfarad capacitor is 20.3 microcoulomb. Looking at step 0, since the charge will be the same on all the capacitors in a series circuit, if the charge on CS is 9.53 microcoulomb, then this must be the charge on both the 3 microfarad and the 5 microfarad capacitors. As we now know the value of capacitance and the charge on all the capacitors, we can calculate the voltage across each capacitor using the formula. V1, the voltage across the 2 microfarad capacitor, equals Q1 divided by C1. Substituting values, V1 equals 29.8 times 10 to the power minus 6 divided by 2 times 10 to the power minus 6, which equals 14.9 volts. V2, the voltage across the 3 microfarad capacitor, equals Q2 divided by C2. Substituting values, V2 equals 9.53 times 10 to the power minus 6 divided by 3 times 10 to the power minus 6, which equals 3.18 volts. V3, the voltage across the 5 microfarad capacitor, equals Q3 divided by C3. Substituting values, V3 equals 9.53 times 10 to the power minus 6 divided by 5 times 10 to the power minus 6, which equals 1.91 volts. And V4, the voltage across the 4 microfarad capacitor, equals Q4 divided by C4. Substituting values, V4 equals 20.3 times 10 to the power minus 6 divided by 4 times 10 to the power minus 6, which equals 5.08 volts. As a capacitor is charged, it stores energy in the form of an electrostatic field, energy that will be recovered when the capacitor is discharged. Consider the circuit shown. When the switch is closed at time 0, charge will flow into the capacitor until the voltage across the capacitor equals the supply voltage. Vc equals Vs. At this point, the current flowing into the capacitor will be 0, and the capacitor will cease to draw power from the supply. Looking at the chart, this process happens over a period of time t seconds. The power consumed over this time is given by the formula P equals V times I. However, the average value of voltage across the capacitor during that time will only be half the supply voltage, so V will equal V divided by 2. The current that flowed over the charging period may be determined by dividing the total charge Q stored on the capacitor by the time taken T. So I equals Q divided by T. And the amount of charge stored can be determined from the basic formula Q equals C times V. Substituting these values for voltage and current back into the power equation, P equals C times V squared divided by 2T. Since energy equals power times time, if we multiply C times V squared divided by 2T by T, the T's cancel, and we get the result shown in the highlighted box. Energy stored equals a half times C times V squared. Provided the capacitance is in farads and the voltage in volts, then the calculated energy will be in joules. The following example is in the accompanying workbook, Capacitive Circuits, Stored Energy. In this example, we have been asked to calculate the energy stored in a 20 microfarad capacitor with a supply voltage of 70 volts. We know energy stored W equals a half times C times V squared. Substituting the values, W equals a half times 20 times 10 to the power minus 6 times 70 squared, which equals 49 millijoules.